Hello everyone. So the topic of presentation is methods for regularization. We will be discussing four methods: least square, L1, L2, and a mix of these two. So this is useful in polynomial regression where we need to fit the data into a polynomial basis, x, x square, x cube, and so on. And we will require high degree polynomials if we want to perfectly fit the data with very low error. But the issue with high degree polynomials is that when we try to exactly fit the data, we obtain a certain set of coefficients that are very high in value, so that at any point apart from the training data, we have very high values estimated, and thus we have overfitting or overshoot in the data. Therefore, we use regularization techniques that prevent overfitting or overshoot. So we'll be discussing three regularization techniques in addition to the normal least square fitting over the Google Trends data of search term camera, and we use a degree 10 polynomial to fit the data. So the normal approach is the ordinary least square, where we minimize the error between the estimated term and the given data, and we obtain the coefficients. But the issue is the coefficients are very large and they are sensitive to training data, so they overshoot in any other point. But the pros are it is the best fit, offers the least error, and it is very simple to implement without any tuning. In order to prevent the overshoot, we use regularization techniques. The first that we discuss is L2 regularization. So the basic idea is to add the coefficient into the cost function, so that while minimizing the cost function, we also minimize the coefficients. Here we are using L2 norm for the coefficients, therefore we have W square, hence the name L2 regularization. The effect is while minimizing the cost function, the coefficients also reduce, and they are not very high because it is a part of the cost function. And the pro is it handles multicollinearity well, meaning when the coefficients are correlated, which is the case in polynomials, x, x square, x cube all are correlated, and it is stable in presence of this. But it does not perform feature selection, meaning all the coefficients are present, and we do not have any zero coefficients. Let's say if we wish to specifically characterize the or fit the data using a particular set of bases, let's say x square, x cube, and x power 7, it will not happen because it will assign weights to all of these terms, so it will not perform feature selection. Next is L1 regularization. Here we use the L1 norm, which is norm of mod of Wj in the cost function, and the benefit is because it can force some coefficients to become exactly zero, not tending to zero as in the case with L2 regularization. And the benefit is it performs feature selection, meaning if the data is having a particular feature, it has a certain x cube trend along with an x power 7 trend, so it will only fit the data into x cube and x power 7, not in the other terms, so that we have segregation between the data. And it can be erratic if the features are correlated. Let's say x cube and x7 x power 7 are correlated with one another. So in order to prevent that, we use hybrid, which has both L1 and L2 penalties, and it has two parameters, R and lambda, to tune. So it has the benefits of both of these methods, but then you have to tune two parameters, R and lambda, to get the best fitting, so it is computationally expensive. So this is a summary. OLS gives overfitting, has no feature selection. L2 has no feature selection, but it is smooth, it does not overshoot. L1 is also does not overshoot, but offers feature selection. And Elastic Net is balanced between Liss and Razo, Ridge and Lasso, and offers feature selection but is computationally more expensive. So regularization is mandatory to prevent overfitting over other data points, and we use Lasso if we suspect many features. We use Ridge if we suspect only few polynomial terms, let's say x cube, x power 7 specifically. And we use Elastic Net if the data set is complex and we wish to obtain both the pros of Lasso and Ridge. And we use the regularization technique over the Google Trend data. So this is a code demo for the algorithms discussed. We use these libraries in order to get these functions for OLS, Ridge, Lasso, and ElasticNet. We use a degree 10 polynomial and the Google Trends data to fit. And we use alpha as 1e minus 3 for Ridge and Lasso, and we have these two parameters for R and lambda. For ElasticNet, we have two parameters to tune. And the dots represent the actual data. Blue is the OLS, which offers the highest R2 score, meaning it fits the data in the best possible way. 1 meaning the data is fitted as in 100%, and all the others mean that the data is fitted up to 30%. So Ridge, Lasso, and ElasticNet offer less accurate fitting, but then they offer benefits as discussed in the slide and do not overshoot, and may or may not offer feature selection. And OLS offers the best fitting, but at the cost of very high coefficients. So the next code is to compare the coefficients. As you can see, OLS has very high coefficients, which will lead to overshoot. Ridge has no feature selection. It has non-zero coefficients for all of these terms. And Lasso offers feature selection with the 0 as the coefficients of the terms that are not very important for the data. So it offers feature selection, forcing coefficients to be exactly 0. Next up, we have an animation to see the effect of the tuning parameters alpha over the ridge regularization. So as the value of alpha increases, the penalty in the cost function increases for coefficients. So as the value of alpha increases, the coefficients ought to become smaller and smaller in order to minimize the cost function. And as for very high values of alpha, the coefficients become very low, and the fit converges to a constant value. So as we increase the value of alpha, the curve flattens and eventually becomes a straight line centered around the mean of the data. So we need to choose an optimum alpha in order to best fit the data to its regularization. Thank you.